Well, let's have another science lesson on reflecting and refracting. Yesterday's lesson really focused on reflecting. Today we're going to watch a little video about telescopes, and we're going to see how refraction or refracting is used in telescopes. Have you ever looked through a telescope? I have a few times, not many times, but they're really cool to see things up close. And how does that work? How does a telescope use light and lenses and all the different things we've been talking about that allow us to see something really, really far away look really close to us? So we're going to learn that in the video today as we're talking about light. Speaking of light, there's lots of light coming in my window on my face this morning. It's a beautiful day as I'm recording this for you. And the sunlight just lights up the whole room and comes in the window here in my classroom. So it goes well with today's lesson. But anyway, let's take a look at today's video on refracting. I think you'll enjoy this. Now, you'll want to pay attention, and you might want to go back and rewatch it, because after the video, you're going to have 5 questions to answer about the video. So pay attention to it, and you'll be at easy 100 on today's assignment. So here we go.
It's amazing to see Shoshone Falls, especially when viewed through an optical device like this, which is engineered for viewing nearby landscapes. But what do astronomers use to explore the nighttime sky? You're about to find out. Hi, I'm Michael Despezio, and welcome to Video-Based Projects. In the 1600s, Galileo developed the modern-day telescope. And ever since, scientists have used this tool to look beyond the reaches of our atmosphere into space. And they have uncovered some of the most remarkable discoveries in modern science. To learn more about them, I'm heading to an observatory in Twin Falls, Idaho. You are in for a treat. We're at the Herritt Center at the College of Southern Idaho, and we're about to meet astronomer Chris Anderson. Come on. Did I tell you this was going to be awesome? Chris.
Welcome, Michael.
Hey, tell me about this place.
This is the Centennial Observatory Dome, home of our telescope.
Say you wanted to look at Saturn.
Oh, one of my favorite targets.
What would you do?
Well, very simply, we have a computer screen that shows us the entire sky. We click on the target we want. The telescope goes there, and it does so with an accuracy of hitting a dime with a laser pointer from 5 football fields away.
Well, 5 football fields away. Now that is pretty good accuracy.
Here's the computer we use to control the telescope. So this is the entire sky. Saturn is up tonight, so all we have to do is click on Saturn, tell the telescope that's where we want to go, and in 20 seconds or less, it goes.
You're kidding. So you just sent the control to move the telescope from here. Oh, I hear something.
That's the dome.
Look at that. That is amazing. And the telescope's moving as well.
And as of right now, it's pointing at Saturn. You want to take a look?
I would love to.
Go ahead.
All right. And look right through this.
Right through the eyepiece.
The eyepiece, and whoa! That is incredible. I am looking at Saturn, and I can see its moons as well. I can see the ring, and I can see the moons.
Can you see the rings?
Yeah, I can see the rings, and there's a couple of really... Seeing a live image of Saturn through this telescope is fantastic. But check out these close-up images from spacecraft that have passed by the outer planets. How is this engineered?
Well, really, a telescope is all about bringing light into your eye that normally wouldn't get into your eye. We've got to steer that light into a new direction so it comes into your eye.
When we think of telescopes, we normally think of 2 main types for the visual light spectrum. A reflecting telescope uses mirrors to focus light. A refracting telescope focuses using a convex lens. In a reflecting telescope, light enters the end of the telescope and travels all the way down the cylinder and hits a mirror. It is then reflected back towards the source of the light, where another mirror catches it and focuses the light into the eyepiece.
Well, this one uses a mirror. So this is a reflector telescope. 24-inch mirror down here. Light comes in the tube, hits the mirror, begins to come together to a secondary mirror up near the top, and then all the way back down to the eyepiece.
But you seem to have another telescope right here?
Yeah, now this one is not a reflector. This one is a refractor.
A refractor, which means what?
Which means instead of a mirror steering the light, this one uses a lens.
A refracting telescope uses a convex lens to focus and magnify light without the use of mirrors.
So the light comes in the top of the tube, hits the lens right away, not like the reflector that goes all the way down to the bottom before it hits anything. And at the very top, through that lens, begins to come together once again. In this case, instead of having an eyepiece, though, we have a video camera.
So I can't look through this directly, but we've got a feed right here.
Yes, we do.
And can we see what it's picking up?
Right over here.
All right.
This is our live view of Saturn.
Amazing. So now we have a TV picture of what we're looking at.
1, 2, 3. Those are all moons of Saturn.
You've explained to me how the telescope is engineered, but what about the mount? Does engineering go into that as well?
A lot of engineering.
Tell me.
Come over here.
All right. What's this?
Well, this is the telescope mount. This is what supports the telescope as it moves and tracks targets through the sky.
It looks pretty sturdy. Can I move it?
You'd have a hard time. This telescope sits on 150,000 pounds of concrete, a pier that goes all the way down 13 feet below the ground and sits on our local bedrock.
So engineers have to really design a sturdy structure that doesn't move at all.
Yeah, because when we want to follow a target and keep on it, especially if we're taking a photograph, any vibration would blur the photo.
So that's not at all transmitted to this.
Not at all. It's not attached to the building in any way. In fact, this mount is built to this particular location on Earth. So this telescope would only function here. Move it north or south, even a few miles, it would no longer be able to track. This tilt is our latitude.
Hey, can we take a look at some other telescopes?
I've got plenty to show you.
Let's see. Looks like we've got quite a few telescopes to look at here. Why don't you tell me about this one?
Well, this is a reflector. So again, the light comes in all the way down to the bottom where the mirror is. Now the mirror has a shallow dished-in shape to it, what we call a concave shape. That means that when the light comes in parallel, after it reflects off the mirror, it begins to come together to a point. Well, if we just did that, it would go right back the way it came. We don't want that. So we've got a 45-degree angle mirror inside that sends the light out the side to where the eyepiece is.
Let's take a look at another one.
Okay, this is a refractor. So instead of a mirror, this one uses a lens. Light comes in here, hits the lens, and the lens is shaped in a convex shape. That means it's going to start coming together as it passes through that glass all the way down to where the eyepiece is down here.
And what about our final one?
Well, this is a hybrid telescope. So we have both a lens and a mirror. It's called a catadioptric telescope. It's a bit of a mouthful. But you can see the difference here is how compact it is. These are really portable. And that's important. We live in a time when 90% of the world's population lives in a place where they can never see the Milky Way. If they want a dark sky, they need to drive somewhere, which means they need a portable telescope they can take with them.
Chris, thank you so much for showing me all this about telescopes. And now it's your turn. Use what you've learned about telescopes and their design in this next engineering challenge. No matter how complex or large a telescope is, its ability to make distant objects appear closer is basic physical science. Okay, here's your challenge. Using the materials supplied by your instructor, which just might be lenses, mirror, paper, build a telescope. First, you'll need to research this topic. Use print resources, online resources to learn more about telescopes. Once you've got an idea of what you'd like to build, make a diagram, make a blueprint. Then build your model, test it. If it doesn't work, that's fine. Improve it, because redesigning is all part of the engineering process. Once you have a final product that you're happy with, communicate it. Show others what you've built and communicate what you've learned in this video-based project.
Okay. So I hope you enjoyed that video. Pretty interesting. You know, the stuff we're learning about in science is not just textbook words. It's stuff that's real life. It's things that that scientists and people everywhere use. Anybody can buy a telescope and use it. So, the lenses that are in there, the mirrors, the reflecting, the refracting, all those words that we've been studying in this unit, they're important. They're real life important part of technology in the world today. And so it's important to know them. That's why we're learning about them. If you'd like to try to build a telescope, research it on the internet. You could probably do it with a paper towel roll and maybe a magnifying glass. Who knows what kind of things you might find on how to build a telescope. So take a look at it. If you'd like to try it and you build a telescope, show us in one of our meets. We'd love to see what you built, okay? All right, there are 5 little questions about this video in the assignment today. You want to get them done before you go on to the next subject. Have a great day.